All right. The theme of this session is structure and computation. I divided the theme into several categories. One is a field body. Okay, field body. So-called field body is atom, like single atom, full electron system, like helium, hydrogen, helium, lithium, etc. Okay, this is actually the important area where you can derive. Okay, you can compare your precision calculation with precision measurements, so you can derive fundamental constants, fundamental physical constants. Okay, so actually this is the one. Okay, the other one is like a system consisting of a few atoms. Okay, this is it's also a field body, but it's getting more and more important because we can control. Okay, using external fields. So it's actually is a important testing ground for ultra-cold physics. This category is also a single atom, but with many electrons. Okay, like Andre probably will be talking about this scenario. Okay, this actually is a playground for testing new physics beyond standard model for elementary particle physics. So extremely important because those effects are proportional to Z to some power. Okay, so it's better to have a large Z, and also time-dependent processes. I think Jack is an expert in this area, and he will be talking about strong field physics. Okay, my first scientific contact with ITAMP actually comes from this email. Not email actually, it's fax message to Jim Babb. I think Jim, you still have that one, right? It is about the expectation value of over the lithium ground state energy. I display here about 6 or 7 significant figures. They are still significant here. Okay, this actually is 1995. Before I came to ITAMP as a postdoc for Alex. At that time, I did some work for lithium. So this I think is still quite memorable. Okay, my field is actually a field body, a single atom, few electron system. Like lithium, for example, I did this, I call it ITAMP, okay? That's from the time when I finished my PhD to 1995. I basically solved this equation. This is long relativity Hamiltonian. Once you got this, you can include relativistic and QED crashings. Okay, perturbatively. So it's extremely important to get psi as precise as possible. So during my 2 years tenure at ITAMP, one of my projects is to derive, okay, or do some reduction of these operators. Extremely time consuming. I spent almost 2 years and finished that. Then with these small crashings, then you can make this energy meaningful when you compare with the experimental measurements, because the experimental values contain all corrections. So after my postdoc at ITAMP, I applied this work to determine nuclear charge radii for so many isotopes. Of course, you have to work with experiment groups. We have Argonne National Laboratory with Zong-Chao and GSI, Darmstadt, has been about more than 10 years. It turns out to be very successful, and this is a review article published last year to summarize all the results we put together. Actually, it's extremely important because, like nuclear physicists want to know what is lithium-11, the structure. Lithium-11 is a halo nucleus, and the beryllium-11 also a halo. So halo structures. So this is a nuclear model independent determination. Okay, so nuclear physicists can get information and as an input to their model dependent calculations. So they can judge which model is correct, which is not. So so I will thank ITAMP for providing my postdoc career at ITAMP so that I can build my move forward to this. So it's important as an early career. So I thank for Alex, Kate, and Rick, everybody at ITAMP. Okay, I also started work. These are also the work that I studied at ITAMP. With Alex is an expert. Okay, in this area. Basically, it's polarizability and dispersion coefficients with Jim, Jose, and also with Gordon Drake and some of my collaborators. This later on will continue. We still work with Jim right now. Okay, so it's and this paper with Alex and Jim and Gordon is actually become one of the most cited in my publication list. It's about dispersion coefficients among hydrogen, helium, and lithium. Remember, some of you might notice that paper. It's also very grateful. And actually, last I want to say a few words about the status of many electron systems. This is a recent compilation from Peter Schwetz's figure from New Zealand. If we look at the dipole, static dipole polarizabilities, you can see, except for few body systems, for many electron systems, it's still not well understood. Okay, so if we look for these, he has a complete list. I only show here, and this is for Jen and Andrew's work. I guess sodium looks good, but most of them are not about two, or maybe digits. I mean, so it's still, I would say, still quite challenging to understand atomic structure. Okay, this is a static polarizability, mostly simple system. Okay, but still for only for few electron systems. That's all. But for many, more than 3, maybe still challenging. So it's a long way to go, but it gives us a hope to work hard to solve problems. Okay, so I think I should stop here and call the first speaker of this session is Jack. Okay, Jack is ready. Okay, let me introduce briefly. Jack was a postdoc, ITAMP postdoc for 3 years. After leaving ITAMP in 1997, he returned to Oak Ridge National Laboratory as a Wigler Fellow. And he continues to work on collision and strong laser matter interactions for a short period of time and switched to the nanomaterials science. He also spent 2 years in Washington, D.C. as a legislative fellow in the office of one of the Tennessee U.S. senators, and currently is director of science of Oak Ridge Leadership Computing Facility. It's a U.S. DOE Office of Science User Facility. Jeff?